Hi, my name's Bob Greener and I'm a volunteer with the Martin Fleischmann Memorial Project. So, happy Easter! This is the day that we all celebrate in the Christian calendar because our sins are forgiven. Okay, so thank you, and for those that are joining us here to find out what I'm talking about today. I wasn't going to do a stream today, but the work that I'd done over the week had stimulated one of the project followers, Alan Cusk, to share some data that he had from a set of experiments, and we're going to talk through those experiments and how they came about. And they are very simple. They can be conducted for less than $100. And so I'll let a few more people come into the room. I'm going to set some things up on the other screen over here. Hopefully the audio is good today. I hopefully fixed it. So can someone tell me if the audio is good today? Okay, I'm going to do some things over here. Just let me know if I have any issues with the audio. I'm hoping I don't. Maybe it's a bit quiet because I've got the microphone over in a different world. Maybe it's a bit louder now. Let me know. Can you see me? Anyone there? Okay, let me set this up. Okay, and we want this. Yeah. Good, excellent. Sound is okay. So, just so that you know, if you ever want to do this kind of thing, what it was is I have a Rode mic here. It's a Rode NT USB mic, and it records at 2 frequencies. Now, when I was thinking about this the other day, I was thinking, hold on a minute, it has 2 frequencies. If I'm broadcasting at 48 kilohertz and it happens to be set somehow in the 4.1 kilohertz mode, then if it's receiving the 44.1 kilohertz audio and it's trying to stretch it, then that would lower my voice and occasionally it might mess up and that would give the glitch. So that was my thinking, and I did a bit of research and I found that not in Open Broadcaster software, but in the software that is the driver for the microphone, you can actually set the sampling rate in there. When I change that, it's all good. So excellent, fantastic. Okay, so what am I talking about today? Well, back in 2019, you might remember that I went on a project Omar, and this was a project to go and test the vibration technology and the Omarza gas of one Dr. Royshin Omarza, and that's why it was called Project Omar. And during that, in preparation for that, I felt that his technology, even though the vibration plates were going at less than a couple of hundred hertz, that they would be producing some cavitation, and that would lead to potentially strange radiation. And I wanted to have a range of witness materials in there that I could take possession of. And I chose one which was a thin foil of indium. The reason is it's basically the softest metal that you can get that isn't going to react violently with water, and also it has most of its isotope is a long-lived beta isotope. So I was going to be testing a large number of potential phenomena, both tracks, interaction with the material, and so forth, and I could take it away and see if there was any radiation. And so there was a lot of tests done, and there's actually a lot more data to share on that. But what happened is something quite special when we came to do the review of the material, and it was a bit of serendipity. And it just is a case of paying attention to what you're doing, and you might find something interesting. And so I'm going to switch frames here. And so what I've got here is the Martin Fleischmann Memorial Project's website at quantumheat.org. And this has a document on here about Ultra, which I called Ultra Affordable Ultrasonic Driven Transmutation. And down the bottom here, you have a link. And if you click on that link, you can view that document here in a full browser window, and you can download it and so on. And what this is an introduction to the rationale behind using indium and the context behind how the Ultra family of experiments were born, and so forth. So there's a lot of information going on here, and so I have experiments using ultrasound in various fluid compositions using various witness materials to see if potential transmutation seen in other experiments could be replicated at a very simple and affordable level. Essentially, Roger Stringham was a pioneer in ultrasound transmutation, and as you may know, also Leclerc. And at ICCF 21 in Boulder, Colorado, Tom Claytor, who you can see there, he replicated the work of Roger Stringham and found the same kind of transmutations that I observed when I was looking at the fuel that was produced ultrasonically in Suhas Raukar's fuel generator. And he came up to me at the ASTI 2016 conference and said, "We're seeing the same thing." And this is a guy who worked for Los Alamos National Laboratory. And he is the guy that at that same ASTI conference was awarded the Preparata medal for proving that cold fusion produces tritium. And he's credited with that in a sort of a Correa kind of corona discharge type setup. And so there's many people that have done this. And so this fed into my thinking before I went on the trip for Project Omar. And the oscillator, the vibrator fins, which I've got over here, I'll just go and grab some Omar vibrator fins here. Here is a typical steel vibrator fin. Actually, this is a steel coated with palladium. So this is a steel coated with palladium fin. You see kind of how big it is. This is a plain stainless steel one here. Okay. And what I figured is it's so approximate and there's so much variance, and there's all kinds of harmonics that can be produced on the thickness, on the width, and the actual tail, that there should be some resonant nodes in here that could yield cavitation. And in fact, you might even be able to see it on this camera. I don't know. Maybe if I switch to the other camera here, you can see these little spots on there. Those are where the cavitation spots are. So as soon as I got one of these plates on the first day of testing in Japan, we found that there was cavitation, and so that was very, very exciting. And in fact, on the palladium plates, it's much, much easier to see where the cavitation spots were, because it went through, and you can see that under SEM there is some transmutation going on. And each plate has a different pattern of spots on it. I'm showing the wrong camera, so that's not very helpful. So you can see there, I'm going to switch cameras actually, because it's just better at doing up close personal. So maybe you can see there are spots on this, and there are spots on this, and they are not in the same place. And this is because there was the right conditions over on the right here, and on the other one there seemed to be all the way across. And of course these were layered like that and vibrating at 179 hertz approximately. And so that gave a very, very fault-tolerant system. And that's what you really want in LENR, is something that is, as I've said with the work that we're doing with the plasma discharges in Vega, is you want a very fault-tolerant system. And so that's as it was. So we'll go back to here. And so I go through the justification for my thinking, because it's got 95.72% of indium and so forth. And you can all read this in your own time if you haven't done it already. And so what happened is, and there's apparatus down here, I'll just skip forward to what kind of happened that led us to this realization that this might actually be a way to do cold fusion. Now, a couple of other bits of context. When you look at the work of Shishkin et al. At Dubna, Science City, north of Moscow, For 9 years, they were doing research, and one of their preferred strange radiation generators was a hydrosonic cavitating rotary generator. And so basically you have a disc, and the disc has grooves in it and holes or whatever, and that spins around in another grooved section, and this produces vast amounts of cavitation. And they characterized the depth and width of pits produced by the captured ions as the strange radiation came out of this device from the aluminium or whatever it is, the actual vein and the steel enclosure and through air or whatever. They showed that this produced a large amount of strange radiation, and in his Sochi presentation in 2018 October, he showed that this is possible, the energy in these structures is possible to kill red blood cells and to cause DNA damage in white blood cells. And this would likely explain why Leclerc at Nanospire and his partner, with only a short period of time with their cavitator system, they suffered for 2 years with radiation sickness, because you end up making very heavy elements and they fission, and this produces standard kind of radiation. Anyway, hopefully that's not what we're producing with these type of devices, because what I'm talking about is this kind of device. So what happened was, Alan Goldwater, a volunteer for the Martin Fleischmann Memorial Project in Santa Cruz in California in the USA, he said, well, you know that bit of indium that you left as a control with me for the indium that you took to Japan, I want to put that in and clean it first to make sure there's no sort of imperfections or rather, sorry, any contaminants on the surface, and then we can characterize the material. So he put it in one of these units, and you can see how big it is with my hand. I've got a big hand, by the way, but anyway, there it is. And these you can pick up for like about $30 US, 35, $40 US. And so this entire experiment I proposed at Madison, Wisconsin University in September, beginning of September 2019, should only cost about $50 to $100 maximum, really, to conduct. And I'll switch frames here. And so this was the piece of indium, and what he did is he put it into the device, and I got someone trying to speak to me here, so don't go anywhere. Right. Let me just kill this. Okay. So he was sorry. Let's go back to the thing here. So he put it in his ultrasonic cleaner, and he took it out, and we put it on the SEM, and this was all within just a few minutes. And he used 4-sodium EDTA, and this is a cleaning fluid, which is meant to leave no residue once you rinse it off. And he used that in there, and it's the kind of thing that you would use for cleaning jewelry or eyeglasses. I think people even use these ultrasonic devices for cleaning, for instance, dentures and stuff like that. You may very well have one in your family or in your home. And anyway, so what happened was he gave me this piece of indium, and I looked at it under the microscope, and I said, Alan, come and have a look at this. And this is what I saw. And when we dug into it and looked at, for instance, this little red spot here, we saw that if you followed the sort of the ejector from the blast here, along the linear track of the blast, it went through various elements. So that there was a lot of carbon, and then after carbon came silicon, and then after that you saw oxygen peaking up to the end here. So this is very interesting for me, because where you have silicon on oxygen here is because I have argued for a long time that the Earth's crust is the experiment that's been running on Earth for about 4.5 billion years. And that is the best indicator, in my view, of what exotic vacuum objects will produce, whether that be cavitation in a fast-flowing stream, or cavitation of water smashing against the rocks on at a beach, or lightning in the atmosphere, or all kinds of different ways, like piezoelectric cavitation from freeze thaw, and so forth. That, sorry, not cavitation, but exotic vacuum object discharge, for instance, if you have quartz in there or whatever, from rock splitting in tectonic shifts and so forth. That if you've got EVOs, then they would tend to produce elements that are in the crust. And what you have here is at the end of this structure, which is largely carbon leading up to it. Now, there is carbon in the EDTA, and there is, of course, oxygen in the water, and so on. But you can see that you're getting this silicon oxygen mixture here, and could it be the fact that it's actually making quartz, and could it be that oxygen, which is the most abundant element in the Earth's crust, and silicon, which is one of the second most abundant elements is the second most abundant element in the Earth's crust, is due to EVO formation, and the fact that the Earth's core doesn't have the same amount of these two elements. Could it be that the necessity or the elements for life are built up through exotic vacuum objects over billions of years, and it's just what will happen if everything is in the right situation? Anyway, this is what we saw. So coming from a situation where we know from Stringham and replicated by the work of what's his name, by Tom Claytor, and the work of Leclerc and people like Cardone, and our own study of the cavitation produced fuel of Suhas Ralkar, we already know that cavitation can do transmutation. And here we see, within a very short period of time, in a very affordable domestic ultrasonic cleaner, we find these huge pits, and only within these pits, or rather predominantly in these pits, do we find structures that appear to have grown from the actual event, and they contain a progression along the length of the structure that ends in something that is round. And could it be that it is being produced by some sort of exotic vacuum object? Anyway, some replication work was done by Alan Goldwater, and you can go and read this. And this is a reference from the work of Takaaki Matsumoto, where Takaaki Matsumoto is saying, very amazingly, it was also found later that on the ring products consisted of conventional elements, mainly carbon, not dependent on the collapsed materials. So he's talking about an electronuclear collapse. And here we see a track in the indium foil replication. We see it starts off small down here, and as it goes on, it gets bigger and it gets bigger and it gets bigger. And at the end, you have what is it? It's a big lump of carbon. But as you go down the track, you have other elements in there. And if we look at that closely and see what is in the track, you can see when there's just a very low amount of an element in a particular area, it gives you the impression that there's sodium all over it, but there really isn't. But in this case with the carbon, you can see the carbon is almost with the entry point, and then it grows and grows and grows, and then at the exit point, when it's having to try and go into the water, it just stops and almost like dumps its carbon. And if you look at the elements in there, it does appear to have aluminium, but I don't think it had aluminium. What I think is happening is you've got the metal here, and it's reflecting aluminium off the support from the sample is on an aluminium support, and I expect that is maybe some sort of contamination from electrons bouncing off and then reflecting back the photons, or and so forth. So I believe we can dismiss the aluminium. We know the sodium in there because of EDTA. We know obviously there's indium in there. But the interesting thing is this end point here, this sample area, gives a lot of carbon. It gives indium. So if it was just a piece of contamination, why has it got the indium embedded in there maybe? But the interesting thing is where you have these bits in the track here as it's going down, you have sulfur. Now, why is sulfur interesting? Sulfur is interesting because we've already shown when we had the 10 yen coin and we had this structure in there, that there were these little balls moving around that were eating the oxygen off the top of the copper oxide, and they were converting it into sulfur. Why is that interesting? That's interesting because ball lightning, if you look at that Chinese observation with a spectrometer of ball lightning, they actually found sulfur in the spectrum. And if you take two oxygen 16s and you fuse them together, you get sulfur 32. And this is often what people report, this kind of like sulfurous, like hell smell when a ball lightning is exploded. And this is some of the anecdotes that you get. So here we have a situation where we've already observed it before. We're observing it in the path that this so-called potential Evo track has made here, which also looks a bit like those, a kind of soft version of what Matsumoto showed, where you have these round areas, these round areas, these round areas, where it kind of like moves a little bit and then does a bit of it action, moves a little bit and does a little bit of action. And so this for me was very, very interesting. And so I presented some of this data at the Madison, Wisconsin lecture that I gave to the IEEE, and some people took up the mantle and did some research. And after the presentations that I've done on strange radiation that have been observed in the Vega experiment using in an electrohydrodynamic system, guess what? I couldn't have wanted for a better set of data. And to be fair to Alan Cusk, he did share some of this at the time, but there was a lot going on, and then we all know what's happened since. And I would like to do some more experimentation with this little beauty with some of the camera technology that we have available now, and also the microphones, and sync all those data packets up together, and also have a radio in play to see if I can see what happens when all of those things are happening at the same time. And the reason is because I'm going to show you something rather beautiful that Alan has observed. And when you see this, you already know from what we've been showing with the Vega experiments that there is a huge amount of low-hanging fruit that people can explore. But there is a large amount of risk with high voltages and needing space and family members to be at least okay with what you're doing. With this Ultra experiment, you're using a device that is used in millions of homes all over the world for domestic cleaning. And you're using it in a way that is not going to break the bank. This is an experiment that uses essentially a thin metal sheet. You can use aluminium foil, normal foil that you would use for food wrapping in your kitchen. So you're talking less than $1 for a good sized piece of material. And the device itself is typically, and I think you can probably use a wide range of devices, but there might be a resonant phenomena. Now, we did some studies, if I go back to this paper, and this is a live document, but if you go down, I did, firstly, when we saw one of these big structures, and I talk about it here, you see these crystals forming in this structure, and it's very interesting. I'd encourage you to read my analysis of this, about how these copper and zinc are found in here, and how they're found, and the crystals they're found, bearing in mind that EVOs tend to produce these crystals. And I'm going to refer back to the work of Duval, where he was exploding titanium foil. And in the titanium foil, he found some iron, but he also found some copper. And in the copper, the copper was producing these beautiful crystals. And this is something that was not in the original starting material, these absolutely beautiful crystals. They just wouldn't have survived for a start. So this is very interesting. And you do see these beautiful crystals forming. And so I'll come back to this when I refer to Duval's work, because it's extremely important what he did in Nantes, replicating the work of Leonid Oroitskiev. So I'll go down, because what I did was, I did some ultrasonic studies of the sound when you have the tank filled at this tank here, and you fill it at different depths. Obviously it's going to have a different sound response. So let me see if I can somewhere here I can find it. Oh dear. Oh, sorry, this is okay, I found it here. Okay, so here are the frequency response. Now, I do want to do this again. Actually, shortly after I did this test, I was looking at the manual for the 384 kilohertz microphone that we have, and I found that actually there is a 20, I think it's a 20 dB switch. What was happening in Project Omar and with the test that I'm going to show you here was that the ultrasonic level was so high that it was clipping the device. And what I did was, through gritted teeth rather, was, I don't know if you can see here on the camera, I wrapped it in bubble wrap to mute the sound. The problem with doing that is that it will selectively dampen or attenuate the high frequency component. And so what you're seeing here is the so-called resonant frequency of the transducer, the PZT transducer here. And you can see it's shifting around when I try different milliliters of water in the tank. But you can also see that there's attenuation above, but there's harmonics. And here is a graph where you can see all of them together. And the interesting thing is when you have little water in there, you get quite a sizable peak in the sort of 21 kilohertz range. And this is actually the same kind of range that Suhas Ralkar was using. He was using 19.46, so it's quite high there. And also there's a peak here at in the blue line here at half that, I guess. And also in the green line, when you are where is that? When you are green, and I think that's the actual operating depth, 600 milliliters. When you're actually at the operating depth, you can see the blue line is still the peak line there, right? And then the green line is actually the bottom. You've got blue, grey, yellow. You can go and look at these yourself, and then green at the top. So when it's got that low amount of water, you've got a very large low frequency component in there, and that might actually be quite relevant to what the observations are. Anyway, so with that context, I'm going to go and show you what was shared with me today, in fact, and because I don't like thinking about things too long, I am again giving you an unscripted presentation. Before I go on to that, I'll see if there's anything you wanted to ask me. So let me have a look. Let me see if there's anything you want to ask. Okay. You know what? Hutchison's work will have a sound component, even if it's phonons. And phonons are, well, they are sound, but it's so high frequency that it is scalar, like sound is effectively. It's like a longitudinal wave, but it's at such a high frequency that it's actually able to interact with the nucleus. Yes, a magic sound, he did use RF for much of his work. The speculation was that where the RF fields overlay, you have or if you have you can use 180 degrees out of phase RF, so that you get stretching and squashing of the vacuum, and that becomes scalar wave, so phase conjugate wave, and this is discussed by Bearden a lot. Anyway, it's great to have you here, Magic Sound, because that Magic Sound, if you don't know, this is Alan Goldwater, and it was his piece of serendipity that led to the fact that a simple device like this, Vibreal ultrasonic domestic cleaner, can be used in this type of experiment. And it's great to have you here, because what you're going to see is, in my view, absolutely beautiful. We've already demonstrated how you can show in an electrodynamic hydrodynamic system what EVOs are. We know EVOs are produced by ultrasonic systems, and we know that they can transmute elements. And what you're going to see today is not only soliton interaction with the material, you're going to see the actual time that it interacts and this track being formed, and an example of a track. So this is an absolutely beautiful thing. So we've gone from no evidence about how these things form and progress to experiments that people can do in their home for very low amounts of money. Okay, so does cavitation create gold in water streams? I would expect that it does. Matter created, boom. Turbines in Hoover Dam move the water, so there's overdrive to okay. Yeah. Bob said Evos create, disrupt, and destroy matter. Yep, they do. Matsumoto says nuclear regeneration. So you put in the nuclear material, and inside the Evo, it can completely reorganize it. If it doesn't completely decay, it completely reorganize it. And you can, he observed elements coming out, predominantly carbon, and I believe I have since demonstrated with very strong evidence from the explosion between a Marsa gas treated titanium and PTFE, and there is more data to share on that this forms in alpha conjugate nuclei. I thought I was doing something original, but of course I wasn't, because this is also discussed by SV Adamenko. So, but we literally have this Evo spike being formed, and at the end it's carbon, and then it's titanium plus one carbon nuclei, one alpha nuclei, and then titanium plus two alpha nuclei, and then titanium plus three alpha nuclei. So you get titanium at the bottom, but then you end up with this sort of I think it was nickel, then iron, then whatever it is. It's 4 alpha. You can go and see that at another time. Is there any way to calculate the mass of an Evo? Well, that's a very funny question, because they can have most of the mass that they started with, to, according to Ken Shoulders, just the mass of one electron, regardless of the amount of matter that they can contain. So, you know, what is the mass of an Evo? Cymatics is important here. Kathy B, what are we talking about? We are talking about creation. We are talking about how creation happened, how you can manipulate it, how you can start with material that's no good to support life and create all of the elements for life, and that it's all around us. It happens in streams, it happens in lightning strikes, it happens when you smash two rocks together, all kinds of things. But what I'm talking about here is where you can have an experiment using a cheap device in your home, and you right now can be at the cutting edge of science. And I'm going to demonstrate how cutting edge of science this is, because people working for the EADS and Airbus, chief technology engineers, not no one, but chief technology engineers, did not solve this when they're presenting in 2015, and the same people have got very senior positions. So I'm going to talk about in this presentation. Okay. Yes, Dan's right. Look up Ken Shoulders. That is an excellent place to start. Ken studied the work of John Hutchison to try and explain it. And he spent... Ken is the reason that you're having this conversation now. He's the father of microelectronics. He designed the initial screening technology to be able to make microcircuits. So the fact that you have an iPhone or whatever, or a computer, or even able to watch this video is because of Ken Shoulders. He also invented the quadrupole mass spectrometer, and we use those devices all the time in our work to determine the elements that may or may not be synthesized in the experiments that we conduct. This is no fool, and he was brought in to work out what John Hutchison had done. He spent the last 33 years of his life on trying to solve that mystery, and that's kind of what we're talking about now, and simple cheap experiments that people can do to be at the cutting edge of science whilst everyone else sleeps. Yeah, LA Flair, this is harnessing the wheel work of nature, in my view. The practical application for me, Kathy, and what I'm focused on is dealing with the 75-year or whatever nuclear waste that's around the world. And this video will probably be demonetized because I've said that word now. But anyway, for me, that's the most important thing. and basically small modular reactors could be put everywhere with zero risk to the population, because they would fail safe, and any waste can be dealt with this technology and families of technologies that are close to it, and convert the radioactive material into harmless carbon predominantly, and extremely quickly. So that is what I'm focused on, and this is something that has been known in certain circles for a long period of time, but people have overlooked it. So this essentially will solve the energy problem by proxy, and then the technology itself has already been described by Ken Shoulders as being able to directly produce electricity, and he showed how, at least schematically, how that should be done, and what he showed schematically is really quite a good description of it. Yes, to fix Fukushima. Yes, because at the moment they have about 1.2 million tons in Fukushima of this tritium-laced water. They can remove the cesium-137, they can remove the strontium-90 because they use like zeolites or whatever to filter it, like a big filter. But they get left with the tritium because you can't separate that from water, and they are hoping that they can dump that into the Pacific, and that has a half-life of over 10 years, and that is not good, because you're poisoning the ocean, and this really should be dealt with in situ. Okay, so I'm going to go on with the presentation because it's very important that I share what has been shared with me today by Alan Cusk. Okay, so first up is I want to share a image by firstly I'll share some traces. So these are the sort of traces we've been talking about in Vega, these spiral traces, and I suggested that might account for the hitherto unaccounted for type of zigzag traces that we see in strange radiation like this. And these ones, which look like a series of plasmoid or exotic vacuum objects woven together in like a braid. And this, you can see it moving here. And this would account for this type of track that's been observed by many people, including ourselves. In this one is a guy called Dmitry Baranov in Russia. This type of trace, where the speed of these traces are the same in both. Width of the traces are the same, however the speed of rotation is different, and if you take the faster speeding one and you just compress it along its length, you end up with a trace that, without changing its width, that is, you end up with a trace that closely matches one that was shared by Jean-Francois Geneste, I think it is. I might get the name wrong, sorry John. And he, I'm going to give you a little bit of his bio because this guy is absolutely no beginner to science and technology. So Jean-Francois Geneste, I'm trying to show you something and you can't see it. Sorry about that. What I was talking about is these beams. So you have this one here. And it's like a helical trace, and this leaves this helical pattern, in my view. This kind of braided one, like hair braid, and that leaves this kind of trace that is done by Dmitry Baranov. And this one is the one that I was describing that leaves this trace that was observed by Deval in 2010 and presented at the European Aviation Defence and so on. And this was published in 2015 by Jean-Francois Geneste, and we're going to come into his presentation now. So Jean-Francois Geneste is currently, this is about as big a title as I could possibly imagine. He is CEO at the World Advanced Research Project Agency. He's CEO at the World Advanced Research Project Agency. And I've met him, he's a lovely chap. I met him a couple of times. You can see him in the front row of my presentation in ASTI in 2016, actually. But before that, before he became CEO of the World Advanced Research Project Agency, he was Vice President and Chief Scientist at Airbus. Now, who hasn't flown on an Airbus? Well, this is the kind of guy that's, you know, looking into air travel and those kind of things. And he was Vice President and Chief Scientist at Airbus from September 2009 to December 2017. So when he gave the presentation that I'm just about to show you a couple of snippets from, He was chief scientist and vice president at Airbus. And so this is not your normal run-of-the-mill guy. And I will get this presentation now. So what I'm referring to is this track here, which he published in 2015. And I believe that in the last week we've demonstrated how this kind of track can be formed by a electrohydrodynamic structure that's formed in what we call the various experiments in glowing activity experiments, Vega. And so I'm going to go to this presentation he has here. So this was given at EADS in 2015 at the EADS conference. And can you see it there? Can you see it? Yes, I think you can. Okay. And the track that I'm referring to is here. So you can see this is the track. And he talks actually in this, bearing in mind this is in 2015. He says, in the following, I shall assume that all those traces and many others which have not been displayed here are from the same unknown origin, and I shall concentrate on figure 6, this one here, figure 6, the one that I believe we've explained in the last week, which seems to be of best quality. Then the only thing we can do is observe. Probably a mistake would be to consider an analytical examination of the trace, considering small parts, infinitesimal, and trying to find a very explanation for that part and trying to build up a global explanation from the sum of local phenomena. So I'm going to look at such a trace as a global phenomenon, and I must therefore wonder whether such a phenomenon already exists elsewhere, somewhere, not necessarily in physics. Rather than a phenomenon, let us consider the trace as a mathematical surface, and let us wonder whether we would not know any similar mathematical surface. The answer to such a question is yes. There exists mathematical surfaces which look like the trace in figure 6. So we'll come on to that. But bearing in mind that this was in 2015. And now let's go and see what he has found in the literature. And to be fair to Jean-Francois Jeunesse, at this point then, and in fact up until the last couple of months, there's literally been no visual data of things forming and acting in the way that these traces could be produced by. There's no electromagnetohydrodynamic structure that's been observed on video until literally the last few weeks. So most researchers have tried to infer what could have caused these structures by the actual aftermath that they leave on witness materials, be that metals, be that ceramics, and so forth. That being said, Ken Shoulders did capture some still photos and even published them in 1986 in his book EV, A Tale of Discovery, which was classified and secret until a good number, about 2 years ago. If you want to find that book, it's on the Martin Fleischmann Memorial Project's Facebook page, and you can type in EV, A Tale of Discovery, and you will get a link to download that book and read it. So he did share some photos of some of these things which he proposed were causing these tracks, but you have now seen video in the last couple of weeks, and today you will also see video of tracks being formed in a hydrodynamic system. In a hydrodynamic system, an ultrasonic system, that we know ultrasonic systems produced transmutation. So here are these structures. Now I have to give him credit because they do actually look quite similar to what might have caused these kind of spirally traces. So you can see here some spirally traces. Here's a spirally trace, okay? Here's a big fat spirally trace here that we have observed in these reactors. And we have also got these kind of general squiggle ones here. But I don't think this explains it all, but I think it was a good shot in 2015 to give this. But you know what he calls it? You know what he calls it? Or what it actually is? It's figure 7, 2 soliton, i.e. there's 2 solitons in there, pseudo-spherical surfaces. 2 soliton pseudo-spherical surfaces. Now, I don't even pretend to know the maths that drew this, but he gives the reference here. And if we go down to the bottom, you can go and buy it. I think it's an £85 book. So let me know if anyone buys it. But it's by Andrei Popov, and it's called Lebedevsky Geometry and Modern Nonlinear Problems, Springer 2014. So the best thing that you could come up with in 2015 is from Geometry that was published in 2014. This is how cutting edge this science is. You have the CEO of the world's DARPA project, basically, and to the best of my knowledge, they don't know how this works. And you are seeing in the strange radiation tracks that we have been sharing, in my view, that Henk and Dave have got out of their reactors and have been able to assemble. You are seeing the tracks that are, in my view, creating these strange radiation tracks. Okay, now what I'm going to do is I'm going to show you a video, and I'm going to play it through first. Then we're going to look at some things that were observed, and then we're going to go through and look at the video again, frame by frame. Now, I hope that the high level of encoding quality that I got on this stream will reveal these items, but I have already shared the link in this live stream description to the video for you to download, and you can look at this on your own computer. I will take out segments and highlight them in the remoteview.icu blog on this video later next week. But for now, I just want to show you the video at full speed. So I'm going to drag this out there, as we have done in the past. Let's see if I can make that full screen. Is it going to show us what we want to show? I'm going to pull that over there. That's going to work. Okay, we can do that. Right. So let me switch frames here. Okay, so let's go to the beginning and we'll play this. So this is a sheet of normal domestic bako foil, like the type that you would wrap your food in, and it is in one of these kind of domestic ultrasonic cleaners, which are about that big. Now, the innovation that Alan Cusk has done is when you've seen videos of these running, the water surface, it has these standing waves all over it, and you literally can't look through it. Well, he did what should be obvious, which is use the glass bottom boat approach, and that is to get something like a Petri dish or some other thing that would suitably fit in here, and put that down on the top, therefore flattening the surface and creating actually a good viewing surface, a flat surface that's even better than what we showed with the ultrasonic system in the Suhas Ralkar's lab in 2017. The video that you can see on the Martin Fleischmann Memorial Project's website called sprites. So you go and look for sprites on there. Anyway, so this is the aluminium sheet, and watch what happens. I'm going to play this all through, but before I do that, actually, I'm going to get it so you can hear the audio, because it helps maybe to understand what's going on in there. So let me just get that set up so you can hear the audio. Give me just 1 second. And what am I looking for? I'm looking for this. So hopefully I can ship my audio out through here. Okay, so hopefully you're going to be able to hear the audio. Let me know if you cannot. Okay, ready. Okay, so there we go. Now we will step through that and I will point out some extremely valuable data. Now this is only taken at 30 frames per second. We have the capability to take that to 240 frames per second. This is only taken at a fairly low res. We can pump that up to a high res, and I hope later in the year, well, we should be able to take it at 24 frames a second at 8K, and we could take it, I think, at 60 frames or even higher, I believe, at 4K. So we'll try and do our best to get the highest resolution on there. But I want to show you a couple of things that came out of this, which I think are very, very important. So when he was looking at the videos that we've shared over the last few days, he shared a track. And before I go and show that track, I'm going to show another thing that he shared, and it is impacts. What he did was he stopped the process very early on and looked at the structure at that point. And he saw several things that I'm going to show you just now, if I can find it. Let me find it. It's not that one. I'm going to find it here. Here we go. So let me show you here. This is a microscope image of a part of the foil, and this foil has spent only a very little amount of time under the exposure to the ultrasonics. But what you can see, and we observed this on the jewel in the Lion reactor, where you had these what I call innies and outies. We have also observed the same thing in the John Hutchison aluminium surface, the sample called fracture. These innies and outies, as I like to call them. And if I zoom into this, you will see very, very, very clearly, because of the way the side lighting is working on the microscope here, that here is the outie here, and we've got a highlight on this side, and here is the innie with a highlight on the opposite side. They are pits with a similar diameter, and then they have another pit in the middle. Is the pit going in the opposite direction, i.e. in this outie, is this an innie, and in this innie, is this an outie? If they are, that would mean that the inside's going counter-rotating to the outside. I would not be surprised, and I've argued in great detail that that may actually be the case. But you can see these repeated, exactly the same. This is actually punched a hole through, and it's punched a hole through here. The interesting thing is that it's not cut all the way through. It's like a travelling wave has punched a hole through here, gone through there, and then gone on its merry way. This would imply, potentially, that it is a helical track like we are seeing here. That might be what has caused... where's it gone now? I've lost it. Ah, sorry. Yeah. That it's caused this. Because if it was a whole EVO and it came all the way through, then the whole thing would have to be neutral, and then it would have to become excited in order to create this structure here. And so we'll zoom out and look at the other one. So this is interesting because just what I've said, where it would cut through, you actually looks like it has cut through here. And you've got this shape here and this shape here. This is the outie, this is the innie. And then over here, you have two that are pretty parallel with an outie and an innie, an outie and an innie. Like it came through here, went through there, came through here, went through there. But you don't see any more. Maybe this was an attempt a little bit further up. I don't know. But here we have, in my view, a very, very clear demonstration that solitons are involved, but quite possibly triangular structures are involved also. Now, the second image that he sent me is an absolute killer. Here it is. This is what excited him and what he shared initially. This looks to me very, very much like what we would generally call a strange radiation track. And you can see that you have a repeating structure here and here and here. And there's another repeating structure here and here, and not so much repeated here. But this does look like it's a spiral structure, and it doesn't look like that it penetrated through the foil. This actually traveled from maybe over here on the left-hand side and went across the track here. Okay, so can everyone see that? Because now I'm going to look at the animation, the video rather, and I'm going to look at specific components of that. But what I am saying is here, you are seeing both something in this image, which, where is it? Not this one. In this image, that it very, very much looks like very clear soliton impacts, or a helical spiral that went through and out and carried on its way. I mean, what might have happened here is a spiral like you see, not this one. If this was going through, you would imagine it would cut a hole through it. But if you had what you are seeing here, and it went through it at an angle, i.e. it wasn't going along the surface, but it went through it at an angle, you might see these kind of structures as one-offs. So the helix is going through at an angle. This might have gone through at an angle where it cut two holes. So this one that looks a little bit deeper here at the top, this was the initial penetration, and then it just went through a little less deep when it went through the second time here. Okay? This one just went all the way through and ripped a bit out. Okay, so this might be these helical tracks that are traveling, helical tracks like you see here on the right, and it's kind of semi-traveling through the surface. Okay, and in the case of the other one, if I can get the image up again, where did I put it? It's over here. In the case of this one, it's actually traveling along the surface but underneath. Okay, so now I'm going to go to the video and I will step through it. So we are here, and what I might do is zoom into areas on this video and zoom and try and make it very, very clear for what I'm talking about. If people can actually let me know if they are seeing what I'm actually showing when I get to show it, if I can actually make this go at a different size. Sorry, excuse me. It's not really working like it should. Okay, there we go. It's listening to me, but not really. Okay, there we go. I'm going to make that a bit bigger down there. Now I'm going to change down as I did before. I'm going to change this in the bottom right here to frames. So you can see I'm currently on frame 0. A lot of animation technology show, or video technology shows the first frame as frame 0. Okay. Okay. So I'm going to step forward with this. It might take a while because we've got 2,224 frames to go. And let me see if this works. Okay, so that's not the best one. I'm looking for something very specific when okay. Right. I need everyone to pay attention. Okay, this is really, really important what I'm just about to show you here. And I think everyone needs to really look at it. I'm going to see if I can zoom in 400% and get this actual key part in frame. Okay, this might do it for us, okay? So what I'm looking at here is this damaged area up here, okay? And I want you to look at the hole where I have my mouse here. I'm pointing that to there, and I'm going to step forward. I'm currently on frame 234. Now, on between 234 and 236, this grey blob comes out of here. Now, when you look at this video, you might reasonably expect to say, or think that it was reasonable to say that the pieces that are grey that are moving around are just pieces of aluminium that have been broken off because of the intensity of the ultrasonic waves. And that may be the case in many of the cases later. But watch this grey blob. I'm following it here. I'm following it here. I'm following it here. I'm following it here. Can everyone see that? Can everyone see this grey blob I'm pointing my mouse at? Just let me know. Let me know. Anybody? Can you see the grey blob? because I might have to do contrast adjust if you can't see it. Can you see it? Hello? Anyone out there? Okay, I'm just going to go ahead and hope you can see it. Yes, you can see it. Excellent. Okay, so we're following this grey blob. Okay? Following this grey blob. Oh, it's changed direction a little bit. Changed direction. I'm stepping from one frame, 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 one frame. You still see it? One frame. Oh my God! Boom! Let's go back. This is frame 283. On frame 284, boom! Right the way across here. It's touched the surface of the aluminium and it's produced a periodic track going across the aluminium. And on the next frame, boom! The same kind of distance spread across. But it almost splits up into two tracks at this point. It kind of hits a pre-existing inconsistency with the surface on the aluminium. And boom! It goes off in two directions. And then what happens? It's going off in two directions and then they rejoin and travel in one direction. Oh my God. Now we're going to see several of these. We're going to see several of these. I'm going to step forward and we'll see. So there's another one down here. Let's go down here. There's one grey one here and there's one grey one here. Let's see if they do anything. Let's see which one does. Boom! Did you see that? This grey one here. Watch, 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 watch. Boom! I'm going to go over there. We'll see this one on its own. So it's absolutely amazing. And it is unidirectional. These things, when they touch the material, the effect happens in one direction. Now, is it the soliton getting wrapped up into the surface of the metal and traveling along it at extremely fast speed because it's drifting around before? Or is it unraveling? Or is it sending a beam of energy as it dishevels, as Ken Shoulders called it, along there? You all have the opportunity to be at the cutting, bleeding edge of science with about, I don't know, $50 of personal investment. That's it. This has been on the table since late 2019. And credit to Alan Cusk for doing this. Look what happens. I'm touching this. Boom! It goes from this little black spot, and this little black spot moves about half the width of my mouse. And the next one, it goes boom, and it goes all the way from here to here at least, and then from here to here, and from here it hits an inconsistency, and it kind of maybe gets shot off. But it's very similar to the previous one. Let's go and see if we see something else. So we got two parts of that track there. Let's see if this little critter here does anything. He's slowing down. What is he doing? He's changing direction. He's changing direction. He's moving around in a circle. Doesn't know quite what to do. He's stuck there. Ready? Ready? Oh, there was one down here. Did you see that? There's one there. Might have been on the other side. And you can see the periodicity here. One dimple, two dimple, three dimple. Watch. Oh, there was one there. That must have been on the other side. Oh, look. You can see it went all the way across there. You see the periodic tracks here? Right. I want this one to land. When is it going to land? When's it going to land? It seems to be happy where it is. Now, I'm suggesting that as this is there, drifting around, it is absorbing bosons of sound. It could be absorbing, if it was in Alan Goldwater's reactor, bosons of sodium-23. It could be absorbing bosons of oxygen-16. It could be absorbing bosons of deuterium. It could be absorbing bosons of 12 carbon. Anyway, let's go forward. Come on, land, land, land. Boom! Look at it. It's fantastic. There we go. It drifts around, barely moving. It's almost stuck in one place. And then suddenly, a massive track. 1, 2, 3. Almost misses it here. 4, 5. And then it kind of goes all the way over here. And it affects the big grey blob over here. Now, what I am saying, I've seen this behavior before in the Suhaus railcar tank, in terms of these things joining together and congregating and aggregating. I think what you're seeing here is the analog of what causes a strange radiation track in the Vega reactors. This is a strange radiation track, or could be, because the energy within those tori that you're seeing drifting around there is getting bigger, it's getting bigger, it's getting bigger, it's basically being pumped, but the thing isn't getting any bigger. And then when it touches the surface, it throws out its guts. Okay? Maybe that's what's happening. Or it breaks, as I've suggested before, and the spiral then flies through the material. Okay? And if you can imagine the same thing going on in the plasma, in the Vega experiments, where you have an energy pumping into an EVO that's just a torus. And I'm going to show you other Vega experiments where you see these tori drifting around erratically, exactly as you see here in this hydrodynamic equivalent. Exactly. Drifting around, not quite knowing where to go. And if I believe that if those EVOs touched a surface, particularly one that was highly charged, doesn't matter, either with ions or with electrons, and touched it, it goes boom, and out it throws a beam. Okay? And it could be that the large structures that you see over here, this grey blob, is what we saw something similar in the Suhaus railcar sprites video, where this is a mass of these things that are forming into a structure and then forming again into a structure and so on. Now, I'm actually showing you something without showing it to you. So this is what I'm talking about. Yes, it's throwing chunks of aluminium around, but this is far more interesting what's going on here. This isn't just what it seems at first. Now, if you have a mobile phone, and I don't know, someone's giving you $35 for your Easter bucks, you know, you are in a position to run these experiments, assuming you've got a kitchen and have some spare aluminium foil, you know, maybe a glass bottom dish, and you can be at the cutting edge of science. Things that the head of the World DARPA project hasn't been able to explain. How cool is that? Okay, so let me see if you've got any questions. Okay, so you're trying to find some documents. Okay, if there's any documents, please go to remoteview.icu. If you haven't been able to track down any documents, put a quick request in there and I'll endeavour to find it. Okay. Yes, the video's in the description. Okay, if the video is blocked, then I will I will post the video separately. I've been given permission to share it, so I will post that immediately afterwards. And what I'll probably do is also put it on our YouTube, and I will also do a slow motion so that you can watch it like very slow. So I think we have the opportunity here to see if when these tracks happen, and bearing in mind, it travels nearly nowhere in many frames, and then in one frame it's traveling a very, very large distance. Okay. Okay. Soliton races from LA Flair. Take your bets. Yeah. BP, you missed. Bestoic Primer, you missed, but you can go and review it. You missed the hydrodynamic equivalent of what we've been watching in the Vega experiments. And Alan Cusk took up the challenge that I gave to the community in September, in October actually, when I published this blog on Ultra, as I called it. Ultra and could this be ultrasonic transmutation or something. Anyway, he took it up. He added a glass bottom boat to the experiment so that he could get a clear video of traces being formed. And this is an experiment that you can run over and over again in very short time frames in extremely low budget. And it's a race is on, guys. It's a race because you have the opportunity to capture video of these traces forming and the structures in much more detail. So, you know, have at it. Actually, that's not a bad idea. Bending specific points in the aluminium foil and then see if that's, yeah. When you actually, I'm going to go back to it. When you look at the beginning of the video here, and I'll go to a smaller magnification so you can see it all here. You notice that you have a whole area in the middle here that's not affected, okay? And then you have a point over here that's affected, a point over here that's affected, and a point over here that is affected. And this is very similar to what was observed when Alan Goldwater had that little bit of serendipity way back when, which I talked about at the beginning here. You have an whole field of non-interaction here, and then these three massive interactions. And I believe what you are seeing is the very low frequency component. Okay, so when you have a resonance, you have resonances on resonances. Okay, so there will be across this diameter. You will have a half lambda resonance in the center, and you also have another one across this diameter. So right in the center of the center, you have two half lambda resonances. Okay, and because this is elliptical, you will get all kinds of resonant modes in here, very cymatic like. Okay, and by putting in different dishes in here, you will affect the resonances in there, by the way. And then you have n lambda plus a half. And so you will get a point here and a point here and a point here and a point here. And then you will get all of the sub-resonances from the fundamental frequencies, from the harmonics, accumulating together. So what I'm saying is that these 3 points were the sum of all resonances. Okay, this is the point where maximum damage occurs to an item in this type of device, and I'm saying that you're seeing something similar here in this aluminium foil. So you have this beautiful clean area in the middle to study, and I guess after a while when you are running at a specific depth, because remember, I characterize that when you run at different depths, there are still a kind of a band over which the harmonics will work, but they do change. But you're still going to get some dead zones, almost whatever you do. And they end up with a dead zone. And the dead zone is what gives you the area you want to study. So at a certain depth and a certain material, you will know where your dead zone is. So you can focus your camera right in on that point and look for features going on. And so as I travel through this, in fact, there's a beautiful area just down here in the bottom. And if I step through this, you get... it's coming from the other side, but you get an impact here. It just produces a lump. It doesn't. I don't know whether it's come through. I don't think it has. But you get a track immediately with periodicity going across there. Then you immediately get another track. Then you get immediately another track. Then another track, and then another track, and another track, and another track, and another. And then it kind of moves around. It's like there's this point here, and it's got locked to the metal surface, but it's excited. It's deforming its own stage. And so that causes it to fan left and right and produce this overall triangular indentation here. And it progressively disrupts it, and then it looks like it's moved at this point, and then it starts to actually eat through the surface here. Okay, so there's so much to study in this with such a simple experiment. Okay, so I'm going to look at your questions again. Whoa! There's too many questions. I've done this under xylene to avoid oxidation of those aluminium bits for making higher energy nanoparticles for aluminium for both catalytic reactions and 3D printing development for aluminium metal. That's interesting, Thomas. Thanks for sharing. Same with my compound nanoparticles experiments for using UV laser to fuse solid where desired to print 3D copper objects. Very nice, Thomas. Thanks for sharing. I think that if, Gordon, you're asking, does it need water, and if so, ionized water? If you are referring to the Ultra experiments, yes, we are using water. It could be deionized water or ionized water. At the moment, the purpose of this video is to show particularly small structures that don't seem to be moving in a very fast way, that seem to be absorbing light, by the way. And as soon as they interact with the surface, they produce very long periodic tracks which have structure, and they look similar to those observed in strange radiation tracks. We have the one track that you can see very clearly here, but it's like a big blue ocean of opportunity here for you to give something back to this science. Okay. Kathy, it's quite possible that this is not known. I mean, I can tell you that I've shared some of the Vega tracks with the actual sort of exotic vacuum object structures, their animations, to the Russian community, and they are jumping up and down. I mean, they have been pulling their hair out trying to solve what this is since late 1990s. So I think what you're witnessing here, it might only be a small audience, but if they didn't publish it, they are also RANs, because they kept it to themselves. And this is the point. You are seeing what has only been revealed publicly, as far as I know, and no one, not even the people that research this most, have anything to counter that. The only person that shared anything like a video is Bogdanovich. In May 2019, of a toroid moving across a surface 2 days after a plasma flow electrical discharge into a metal plate. And so the glowing object is on the metal 2 days after it was exposed. And a video that he claims is a video, but we've only got a still of a crystal-like structure made of these toroids, but which the little toroids rotate around their own axis, as does the group body, rolling or translating across the surface. Those are the things that they've shared, but neither of those two things are showing tracks or structures that could form the tracks. What's happened in the last 2 weeks, or maybe 3 weeks at most, is we've been able to share from researchers in multiple countries a magneto-electrical hydrodynamic structure formation, a range of structures, their interaction, and that they are of the form that would explain the strange radiation tracks that have been observed over the last several decades. and hitherto unexplained. And we've shown in this, I believe, in this ultrasonic experiment, this very cost-effective, low risk relative to the Vega experiments, experiment that can actually show in a hydrodynamic analog, although ultrasonics has been shown, and we have observed it also, to create transmutation in several systems and been replicated by people that worked at Los Alamos National Laboratory. They've shown the transmutation, but they didn't know what was causing the transmutation. If they did know what was causing the transmutation, they have not published it, and they are also rands. It's them keeping things for themselves. They have not published it. We are seeing for the first time right today is a magnetohydrodynamic hydrodynamic equivalent, I believe, and I think it's open season on getting the best images with this. Okay. Yeah, okay, so thank you, Alan Goldwater. I know some people had a lot of problems getting this Vivreal device when we first proposed it as an experiment that can be done. But there are many ultrasonic devices. And if you go and look at the blog on this, there are a number of two devices which were very similar in terms of the transducer. They tend to be in the 30 to 40 kilohertz range. And I believe you could achieve this effect with pretty much everything. It would be interesting to see if people can't achieve this effect, but it is punching soliton holes in here. There are structures that are storing enormous amounts of destructive capability which they release on touching a surface. That is without a doubt. That is 100% certain from what Alan Cusk has shared with me this morning and I shared with you this evening. 100% certain. What you are seeing here is what can happen if the conditions are right. But I believe, just like I observed with Project Omar, with looking at Dr. Ruishin Amaza's vibrator plates, this is very fault tolerant. Somewhere there will be the parameter space that is suitable for creating these effects. What do you need to buy? An ultrasonic domestic cleaner you can get off eBay, you can get probably at your local electrical store. When I was looking through these online, I found out I could just walk down to my local hardware store and my local electric store and get one. They're used for cleaning dentures, they're used for cleaning jewelry and watches and eyeglasses and stuff like that. So this is not something that is not easy to get hold of, and they are really very affordable. And you don't need them to be super powerful. This isn't a lot of watts. I think this is, what does it say? This is 35 watts. 35 watts. Okay? It's not a lot of watts. And it doesn't matter if it's at 60 hertz or 50 hertz. Okay. Oh, and you need some aluminium foil and a water that has tap that has water in it, and then maybe something, a glass bottom, like a glass baking dish might be suitable. You put that down and then you mount your camera up and you're good to go. Is this related to the Big Bang? Yes. Many authors, and I would agree with this, starting probably with people that were researching the work of John Hutchison. So John Hutchison did this experiment based on Tesla's work, which he expanded by introducing a lot of electromagnetic equipment that he acquired, but wasn't available to Tesla when he was doing these experiments. And he created what he called this, or what others called this lift and disruption system, which did a range of amazing effects. Ken Shoulders was brought in, and also another person that worked with John Hutchison whilst he was in Canada was George Hathaway. And George Hathaway concluded, and I found this out after making this realization that this had to involve magnetic charges or something akin to it, that George Hathaway had concluded that magnetic charges were involved, and that was in the 1980s as I understand it. Magnetic charges have also been quoted specifically in the Soliton patent applied for in October 1992, and then later down the line people like Roitskev and Bogdanovich and so forth. Bogdanovich works for the Russian Nuclear Physics University in Moscow, and Roitskev is another researcher that did his exploding foil work in the Kurchatov Institute in Moscow. And all of these parties believe there's monopoles, and when you get monopoles of a certain strength, they can get to the point of unification of the forces, which means that your weak force, your gravity, your electric force, and everything, the strong force, they all come together. And this is the state at which the birth of the universe is meant to be in, when all matter was created. So you're creating little miniature new universe births. Each time one of these structures firstly forms to a level where it's organized enough, and then it self-collapses, and then it goes poof, like a supernova, and you get all the elements in the periodic table being synthesized. No, you do not need a Hadron Collider to synthesize elements out of what you have available. So Thomas, that's great if you can produce custom devices. He's saying that he can produce custom ultrasonics, but you can just to run these experiments and be at the cutting edge of science, you can just go and get something that costs a few tens of dollars. Well, there you go, Kathy. Your dentist uses one to clean the your mouth guard. So why don't you go to your dentist and say, sorry, but I've got to do a cutting edge experiment. Please, can I borrow your ultrasonic cleaner for a few minutes? I'm just going to put some baking foil in there. And I just want to get my mobile phone out and a Petri dish. Don't worry about the Petri dish. It's just acting as a glass bottom boat. I just want to do this experiment. It's going to take, I don't know. If you've got 3 minutes you can spare, let me have 3 minutes and I'll run a couple of experiments and then you can have your cleaner back. Thank you. Bestoic primer, let me know what you find at Walmart. Yeah, again, essentially, if you look at the live document that is available at quantumheat.org under the moniker Ultra, that's ULTR, and even in the description of this video, you can go and see the live document, and in there it shows you a breakdown of two of these commercially available devices, and you can see they've literally got an ultrasonic transducer of between 30 and 40 kilohertz, and they've strapped it with a good epoxy resin to the bottom of the steel dish. So there's the steel dish, and that's it. That's basically your device and a driver circuit. This is quite nice because you can set a particular time. So if you wanted your experiments to consistently run with a known parameter space, you can say, like, I'm going to put 200 ml of water in there, I'm going to put this much aluminium in there, and I'm going to run it for 90 seconds or 2 minutes or something. And so you can have some control on that part of the parameters. Bigger isn't better in this situation. What you are looking at an experiment. What I've shown you today, this experiment here, is done with a device of the type that I'm showing you here. Okay, so I think more data and higher spatial resolution. By that I mean not 640 by 480, but ideally 8K if you can, or 4K, in focus and with as high a frame rate as possible, and ideally with global shutter if you can do that. And therefore you get registration of all the key factors that are going to give you more detail and understanding about what's going on. And then if you can get yourself one of these Narugu microscopes. Now I would suggest this doesn't work very well with modern cameras. It's actually better with a Sony
I think it's an 18 megapixel camera on an old Sony phone, or the camera that's on a on a Samsung S7. So you can go and pick up an old S7, probably for about $40–50, maybe one. It doesn't matter if the screen's broken. You don't care about that. And then you strap on one of these little beauties. I'll switch to this camera. This little beauty, you put that on there, and it channels the LED light, and then this is claims to be 400 times, I think it is, magnification, and this will give you an extremely detailed look at the structures that form on these aluminium sheets. Yeah, I mean, my suggestion, Thomas, was to use all kinds of foils. I started with indium because I was interested in the fact that the majority of it is a beta isotope, and exotic vacuum objects are meant to, by some authors, produce cold neutrinos, and they can stimulate the decay of the beta particle, the decay of the beta isotope, yielding electrons which would feed the EVO. And so I hypothesized that if I had a small window of exposure to a device that produced cavitation synthesized exotic vacuum objects, that I would want something that was very susceptible to transmutation. I believe that would be the indium. But aluminium is a very good example because it's cheap and it's already been proven to be highly susceptible to LENR in that it actually has a high NMR nucleus, that's nuclear magnetic resonant nucleus, which means if you had a monopole approaching it, it's going to want that nucleus, and if it strips off all of the electrons and just grabs that nucleus, because it's a fermion, it won't want to be in the nucleus, in the core of the exotic vacuum object, and if you get two of them going in, you typically get production of silicon and magnesium either side of the aluminium, and this was observed in the Hutchison fracture sample, and we've shared that data before. So aluminium is highly effective. It's also, I've said this since the beginning of 2017, it's highly conductive, so there's plenty of free electrons, so they're easy to give over to the exotic vacuum object. And also the melting point is low, which means it's the bonds between the metal lattice atoms is weak, and so the whole structure can be manipulated by the EVO easier. And so aluminium foil is, for me, probably a very, very good material. It's cheap, it's available, you can get it in a range of thicknesses, and it has these known interactions with many John Hutchison and related LENR technologies. That's a good tip about tuning your reactor. You can actually buy the transducers extremely cheaply. You can buy just the transducers on their own. I'm responding to Thomas Anderson talking about how to construct it, which is useful if you wanted to make custom transducers at a particular frequency. If a nickel screen was used, Conscious Energy is saying, would it be more definitive than aluminium? You know what? It's a blue ocean of opportunity. Why not have a look? Why not try it? Aluminium, as I've said, for the reasons I've just given, is highly effective in interacting with these kind of structures. Does observing the experiment change the results? Well, certainly when you place the petri dish or the glass bottom structure into the Vivrial or whatever your ultrasonic cleaner is, it will change resonant modes. And so you kind of, to control that, you want the known amount of water, you want to press it down a certain distance. And you can see in the sprites video, Suhas Ralkar, that the behavior of the sprites is different when it comes to the surface. So there will be a difference here, but there is water between the bottom of the glass and the aluminium, and then water underneath that. So that isn't really that important. What you are seeing is a replication, in my view, in hydrodynamics, at least of what may be happening in the magnetohydrodynamics in the plasma. But we know that cavitation does produce transmutation and strange radiation, and so it's quite likely that it's doing the same. What it is creating coherent matter, coherent energy. So I believe those tori that you're seeing, these little grey blobs that are moving around, they are collecting coherent, they are cohering energy. In this case, almost certainly sound, and because they get so energetic, they are able to rip the water molecules apart, they are able to rip whatever else is in there apart. You can see them ripping the aluminium apart. If you get enough density of the energy and enough compression, normal magneto-electrical hydrodynamic structures, Lutz Jätner, a German researcher, he calculated that the density inside the torus was about 5 times that of the inside of the sun, the center of the sun, and about equivalent, I think, to a pulsar, and it has a 50 million Tesla field, and so it's not surprising that you can get very exotic effects. So Dan Moretti is saying, is quoting Tom Bearden, and I have his books here. So this is Tom Bearden's Oblivion, and this is Tom Bearden's Third Alliance, and that is the chappie that he's referring to there, and he's calling these ghosts or vacuum engines. Ken Shoulders referred to exotic vacuum objects as the universal clutch, that they allowed you to interact with the vacuum, whatever that might be, and interact between matter and other matter, and get everything involved. If electrons shouldn't come together, but these things allow electrons to come together, and not only just come together, get close to each other, that it allows the unification of the forces. So, I mean, you can't get more clutchy than that. Are you really hard to? Am I really hard to hear? Oh dear, we're back to the audio that's in tune. Am I louder now if I get closer to the microphone? Sorry, Dan. Oh, with the video running. Let me kill. Okay, let me do this. I'll kill the audio here on the video. Let me kill that. Okay. Oh, I don't know what's going on there. It's having some issues with the playback there. Sorry. I don't know whether you would see any radiation with this, apart from strange radiation, which, as we know, is not so easy to see. And when we tested the indium in the Omar vibrator plates, we didn't see any emissions after that. And the reason I wanted to do that is because indium is actually a known neutron absorber, and if it does absorb neutrons, then it has an M state, an isomer, not an isotope, an isomer, and that produces a photon, and I think an X-ray. I think it's got a 50-minute half-life or something. So this is the way that you test neutron activation for things that are producing neutrons. So I wanted to do that, in part because he had these palladium foil in there, palladium coated vibrator plate. So if there was standard sort of cold fusion type reactions going on, where some people claim that you have these neutrons coming out, but the Russians call them pseudo neutrons, and they are actually cold strange radiation. Anyway, that's beside the point. Then I wanted to be able to see if I was seeing the those photons, that ionizing radiation coming off, but we didn't see anything above background. Alphas and betas would be absorbed by the water, yes, those that are emitted at the time. But low energy nuclear reactions tend to take anything radioactive and make it stable. So, you know, when the EVO has done its work, it's more stable. That's the whole point of using it for radiation remediation. By using it for radiation remediation, you're taking cesium-137 with its 30.1 year half-life, and strontium-90 with its 29.7 or whatever it is year half-life, and all of those other plethora of beta isotopes that come out of fission of uranium, and make those stable. That's the goal there. Why are we using bismuth? Would be interesting. Yeah, it's a diamagnetic material, and you know, that would be a great one to try. So have at it. It's also a very low melting point, so not that may be the same in this case. I've argued that bismuth is the material that you would want to coat a anti-gravity craft. If the anti-gravity craft had anything to do with exotic vacuum objects, you would want to have the most diamagnetic element that there is used in your device. A magnified glass for the cover. That's not a bad idea, LA Flare. Yeah. That's not a bad idea. I'll give a different view. Okay, I'm going to go in a little while. So if there's any specific questions for me, throw them into the live stream blog. Measure the weight of the foil and then measure the weight of the residue after to see the test to see how much aluminium disappears. That's not a bad test. I mean, there's obviously a lot of issues. You might lose a lot of water in the process, and yeah, okay. So you're looking at the residue. It might be worth it. After maybe if you did 20 tests and then lowered increased one of the figures, you can maybe get a more accurate idea. Have you tried doing this experiment with dry ice and alcohol to observe what might be happening in space? That's not necessarily a bad idea. It might be interesting to try and see if you had like dry ice in water and then ran the experiment and see if the EVOs are leaving the surface of the water. That might be interesting. Try and capture them in free space. Yeah, running through some dry ice. That's easier for people in the States who can just go to their hardware store and get some dry ice. It's not so easier
easy in other locations. Yeah, Hutchison worked with levitation. This is true. Yeah, humidifier. Funnily enough, Bestoic Primer, humidifier are ultrasonic. Yeah, the clusters are pulling in particles to them, but are the particles being carried by other solitons? Who knows? Or clusters. So it's totally fascinating to study. Wow, thank you, Kathy. That's only, I have to say, that's only the second what do you call it, super chat I've got on the channel. So thank you very much. That's very kind of you. You can get indium foil Bestoic Primer because they use indium as a heat sink material between a semiconductor and you know, the heat sink, and so that's where I got mine from. Pure aluminium would be quite interesting, yes. It looks like the little grey dots are fast spinning clusters of particles, probably made to spin fast by the ultrasound vibrations. Maybe, but I don't know if you saw the first part of the experiment presentation here, but it's when those little grey dots, some of them, hit. So just for those that may have missed it, I will just look at the first one that I showed on this stream. And we need to go and find it because it's a bit near the beginning. So for those that missed it, I'm just going to review it here. Sorry if you already saw it. Okay. So what I shared with people to begin with is this little hole where I've got my mouse here, this one here. There is one of these structures that comes through it at this point, and it travels down here, travels down here, travels down here, travels down here, and I'm stepping forward slowly, and you can see 283 here. It's just been drifting. It's not been doing much. It's just been drifting. And then suddenly, boom. In one frame, it produces this rippling damage to a large area of the aluminium foil. And then the next frame, again, does the same, but it splits into two because it's hit a discontinuity. And then it would appear, after getting to this flat area again, it joins up again. And then when it hits this discontinuity, it dies. And Ken Shoulders described this quite carefully, that he says, like, an Evo can go along and then it can split into two and then it can come back together as one. He seems there's some sort of high level of coherence between them. They're like entangled, and if you put them through a flat between two flat plates, they can split into many filaments, and then all the filaments rejoin at the other end. They're like, they've got a spring between them that holds all of the filaments together. I think you can see actually at one point in here that there was a hair in there, but that's not the important thing. But maybe that changed it. But I think you can do this experiment every day of the week, and you will see it still observe these phenomena. No, you can have a single soliton. But I believe that the solitons are themselves well, you can have a basic soliton, but the solitons have a thing where it goes in and then out, but the out is flowing over the top. So it effectively has, in the hydrodynamic model, it has a very intense pull and a spread out push. And so it's kind of like it has more pull on one side, but if you've got two of them, they come together, and if these then could form a chain, and then you have a soliton of solitons, and then that has its own action, and then I believe those can join together, so they can similarly cluster. Thank you, dear Diodon. You are number 3 on the channel. Thank you.
Okay. Use a magnet to see if the aluminium particles become magnetic. That's a very good suggestion. Thank you, Axel. And again, it's a great big blue ocean of opportunity. Go ahead, see. Oh, yes. Okay. Are EVOs attracted to anything besides other EVOs? If they are charged and they are from zero charge to hundreds of billions of negative charges, they will be attracted to an anode. If they are charged less, then they can go through pretty much anything. However, they can be re-excited such that they will then take on more electrons and go from what Ken Shoulders called black mode black mode to white EVs. And in the white EV state, they will interact more aggressively with matter. And it would appear that EVOs are attracted also to, I would certainly say, magnetic nuclei, and iron 57 at 0.7 of a meter from the exploding titanium foil of Leonid Oroitskev. He was able to capture magnetic north and magnetic south charges on two of these iron 57 foils with the magnets one or other way round, and demonstrate under an NMR device that it had changed the fine structure magnetic moment of the iron 57, and the control piece was as it should be. And so they are attracted, it would appear to be, to ferromagnetic materials. So one reason when we were doing the Vega experiments, straight away the steel reaction chamber was swapped out for an iron one. Okay. Larman Ball, what is the dimension of the foil in the video? So I actually, in the conversation that I had with the producer of this, there were several questions raised, and that was one of my questions. And you can go and read this openly on our blog. And let me just check it's the right one. Yes, it's this one. So I will... So the blog is remoteview.icu, and it's the Vega More Extraordinary Traces. And you can see the conversation I had with Alan Cusk earlier today. So he's saying that, first off, I asked for various specifications, and he says that in his device, the aluminium foil is placed approximately 2 millimeters under the plastic. I will share the screen here so you can read what I'm reading. Placed 2 millimeters under the plastic. You can see my question here. I'm saying, what was the depth of water you found produced the best results? And in his case, it was 70 millimeters depth. He used standard kitchen aluminium foil at 0.01 of a millimeter. He was using a camera that was shooting at 30 frames per second. He says the length of the frame that you see is 50 millimeters, and the mark is 10 millimeters long. So I think he's referring to this mark here. So this mark here, I've actually got a better scale on that. Let me go to the Photoshop image. Where's the Photoshop image? Here. So he's saying that this track here is 10 millimeters. That one there. And the distance between the holes that you see over here. So you have a punch out and a punch in these holes here. And as I say, I think this is a spiral that first hits here and makes a big hole, and then only just about does it over here as it's going through at an angle. and that's my hypothesis there. The distance between these holes, which is the center of that thing, is 0.3 of a millimeter. So that would give you an idea of the overall field effect. And it's very sharp. I mean, you basically have flat aluminium here, and then suddenly it bulbs up. And this actually looks a lot like when you see these EVOs moving through free space and interacting. They do literally nothing, and then it's everything. Okay. Let's see if there's any more answers to my questions here. The frequency is 40 kilohertz and 50 watts. Ordinary clean water and ordinary aluminium foil. Aluminum foil for you Americans. And you can go and ask him questions on there, on that blog. So it's at remoteview.icu and Vega More Extraordinary Traces /comments. And you can sign up to the newsletter and you'll know when the next presentation is going to be made. And believe me, what happens is something comes in my door and I can't be bothered with holding it in my head. So I just kind of have to get it out. So it could be actually at any time. Okay, so there's some discussions there between Henk and I. So you can go and ask, those are the key points, I guess. Distance between holes is 0.3 millimeters. The track was 10 millimeters long. 0.01 millimeter kitchen aluminium foil, 70 millimeters of water in the tank. And it was yeah, so there we go. Okay. What else you said? Is this related to the mysterious element 115? Certainly, John Hutchison was able to do some lift, and certainly Ken Shoulders would say that there's some propulsion. I would say that if you've looked at the Vega videos and you've looked at what I've shown you tonight, you can see there is a highly unidirectional motion when there is one of these traces in effect. And that, he said propulsion's better than anti-gravity because propulsion can work in any place in space, for instance. The point is that our Vega experiments have indicated that the structures may be coherent matter spheres or torids, and that these can form superclusters. But in, for instance, a sphere, the mass and charge inside there is negated, which means you have a means to do an anti-gravity effect or stop the effect of gravity. And I've described this in previous videos where Dr. George Eagley has told me some of the anecdotes that he has in his archives, where one example was a natural ball lightning came into view and it disheveled, it fell apart, and a lot of sand came out. Another example from a different person was a ball of lightning fell apart in front of someone and gallons of water came out. And this is interesting because there's 2 points there. One, that the water was not boiled and the sand was not sintered, which means it's not hot in there. And two, that the mass of those things, if they're floating around in the air, was negated whilst they were moving around. And we've observed something similar and highly magnetic or field interactions between these structures in what I call tungsten chop shop. And it's one of the early videos we shared in the Vega experimental series. For the camera, what are we talking about? Any camera, really. I don't think you can buy a camera that doesn't do 30 frames a second. John Hutchison samples have been known to produce magnetic and even apparently magnetic monopoles, but some of his samples were steel, and if you have austenitic magnetic steel, which is not magnetic, and then it goes through a recrystallization, you can have some ferromagnetism produced in those materials that have changed their crystal structure. But certainly we've seen a range of LENR experiments where things have been produced that seem to respond to a magnet where the material beforehand is claimed not to have done. Well, you say about the real true science and fake science. What I started with this presentation was showing that the World DARPA Project CEO, who I've met, and he's trying to solve these problems, to the best of my knowledge, has not solved it. And the people that built the Soviet nuclear weapons, you know, and I've said that word now, so this will be demonetized. They are jumping up and down at the videos that we've shared of the Vega experiments in the recent days. And they've been desperate to have these are really incredibly intelligent people, scientists that have been doing this kind of work all of their lives. They're jumping up and down at what they're seeing. And, you know, so it's not that they're not trying to, there isn't people in various countries. I mean, Matsumoto's Japanese, Ken Shoulders was American, John Hutchison was Canadian. Many of the researchers that I work with or interact with are obviously Russian. And Geneste was referring to Duval's work, which was conducted in replication of the Russian Roitskev. And Duval is French, and he was working at Fondation de Relais or whatever it is. And they did a whole series of experiments into strange radiation. And when he was head of technology or whatever at Airbus, he was giving presentations on this work being done. So it's not like people at the top level are not trying to solve this. In 2000, Graham Hubler was asked by the BBC to look at the Dennis whatever it is model of ball lightning, and he said, look, we've been very interested at the US Naval Labs in what ball lightning can do and how it can form, and they had no answers that they were publicly going to give at that point. And that guy then 10 years or whatever later ends up running the low energy nuclear reaction research at the University of Missouri, and still he doesn't have an answer. And when I first started talking about Ken Shoulders' work, having not known that Ken Shoulders had presented a long time ago, I think at ICCF 10, trying to get the community to think about exotic vacuum objects, I was kind of felt like I was being laughed out of the room. And it was a few years later that people go, oh, maybe there's something going on here. So even people within the LENR community, it's not that they didn't want to know the answer, it's that they had been stovepiped, or they weren't even aware of Ken's work. And so it's not like necessary that there is a deliberate act to not understand this. It's just that it's so not available to people. But that is changing. It's changing. And it's changing because we can't wait. As I said in the last video, we can't wait for other people to do this for us, right? This is part of nature. What you're seeing in the Vega videos is nature. It's doing exactly what nature does. It explains something that's not been able to be explained for decades, strange radiation tracks, okay? And what you're seeing in this hydrodynamic system is it's a hydrodynamic structure, but it's exactly the same kind of thing that we've observed, and we know these cavitation systems produce transmutation, and that is proven by a guy that worked at Los Alamos National Laboratory, without a doubt. So, you know, let's get over the fact that this cannot transmute matter. It can, okay? And what you are seeing, I believe, in this hydrodynamic system and in the magnetohydrodynamic system are how it's doing it. Metallized mylar might be a great idea because you've got a boundary there, especially if you can get the actual real metallized mylar, the one with the aluminium sheet on one side and the polymer on the other. It's not a bad idea. Thank you, Axel. Good idea. Kathy, there is absolutely nothing more interesting that I believe I can do with my time on this planet, and I've felt that since I started this volunteer work, nearly 8.5, 9 years ago. I don't think there's anything more interesting I could be doing, and that was before the sequence of events that's got us to where we are in the last couple of months, and it's like people have done a lot of effort to try and stop this. Really a huge amount of effort. So it's not like that there isn't things that you could construe as conspiracy, but it doesn't matter. We're ploughing forward, and it is public. And when it's public, people, the most important thing is to look at what's happening and not assume that everything is already known, because there's this wall of people out there that tell you nothing is interesting happening, you don't bother looking, absolutely don't look. And it's like, no, sorry, I'm going to have a look. What's that? And they go, well, I don't know. It's an artifact. No, this is not an artifact. I can tell you right now that Hanks sent a series of other videos just prior to the weekend, recorded on the 2nd of February, that he didn't think there was much interesting in there, so he didn't send them over. And we are seeing some of the more interesting squiggles, these plasmoid structures, these exotic vacuum object structures that have been observed in Dave's work. And so what we have is multiple people with one at 240 50 hertz and one at 120 volts 60 hertz in very different morphological systems, but the key thing is having these brass plates with the gaps between them and over a certain level of voltage, like in the 4 to 5, 600 volt range. And they are seeing exactly the same structures. And why these weren't seen before is people were assuming it's just sparks, because they were they're applying what they already know to what they see. And not expecting anything, and being told that to not expect anything and don't even bother look, and if you do see something, it's not really that interesting. And the other thing is, the cameras probably weren't available to see the resolution, and the other thing is that if you have your exposure such that the whole thing looks like a big plasma area, you won't even see these things because they're inside something that's too bright if you've got your exposure set wrong. And so you have to dial it down so you don't see the overall glow, and you're looking a little bit into the plasma, and then you see these structures interacting with each other, merging, joining up, splitting, rejoining up, and also producing these, not all the time, because it's a statistical variation. If you're trying to, if you've got 1 million people and you want to create some great athletes, you have to identify the people that have the right aptitude for that, the right ability, and then work on them. And you kind of think of it like that. And so out of all that, if you don't get things right, you'll never see any of them. But what is true is that these structures are being observed between different experimentalists, totally independent, and in multiple sequential experiments. So this is very, very replicatable. This means it is science. And what you're seeing with this ultrasonics is science, because it's replicatable and you can be involved. Yeah, Axel, they say it's corrosion. Okay, guys, so I'm going to call it a night. It is 22:40. That is a full hour and 40 minutes past curfew. So I'm going to call it a night. So thank you very much for your time as ever. This has been an absolute pleasure and honour for having the opportunity to share Alan Cusk's work, and thank you again to Alan Goldwater for for just the serendipitous event. And I would encourage people to be a part of science. You know, this is the cutting edge, in my opinion, and this is what will produce alchemy. This is, in my view, what is the mechanism behind alchemy. These kind of structures. This is what will produce propulsion at any point in the universe. This will allow us to rectify mass for propulsion and other means of propulsion, which I'll talk about at a different time. This will allow us to go to another solar system in a reasonable time frame. It will allow us to take habitable planets, and if they haven't got the right elements there, to synthesize the right elements to make an atmosphere and to make the right element ratios for supporting of life, and also produce all the energy that's needed. And in the short term, it can deal with radioactive waste, which enables us to use standard nuclear technology that's well understood. There's no real reason for an energy problem, to be fair. So thank you very much for your time, and I will see you in the next video. Bye-bye for now.